Hello. So my name is Mark Wiebe. I'm currently working at a visual effects software company, ThinkBox Software, but I've done some development within NumPy, and I started the DyND project kind of after a few years of experience with that. And what I'd like to talk to you today about is basically some of the motivation of DyND, where I think it can play a role both within Python and broader, and in particular how the typing system we've designed plays a role in that, and how it's pretty foundational. So, so my overall structure, I'm going to start with a little bit of the premise, like why would you want something like DyND? You have NumPy, you have this huge stack of software on top of it. I'm going to go at that from one particular angle. There's lots of different sort of ways you can think of that, but and then kind of take a step back and consider dynamic array infrastructure as a thing. It's like, I think that's something we want. NumPy is that for Python. Could we do more? And then kind of look at type specifically in DyND. So where did DyND come from? It's really, for me, it stretches back from before I did any development on NumPy. So basically, RenderMan from Pixar is a software that's been used to render like all the Pixar movies and many other visual effects and animation movies. It was written in the 70s and 80s, and its shading language was run in a SIMD interpretive fashion on grids of micropolygons. And you can think of it very much like NumPy arrays and then NumExpert execution on top of it. They're very similar. And so like the kinds of technologies that we have in NumPy is similar and is connected to ideas that were in the foundation of the entire graphics industry and field. So that's kind of like part of the connection I saw and why I was attracted to NumPy. And so I spent many years at a visual effects company in the R&D department called Frantic Films, and we developed a particle rendering system called Krakatoa, and it's based on a general kind of channels idea that is very similar to, say, structured arrays in NumPy. And the flexibility that you get from just being able to name a channel and what type it is, and building on that, we had our various systems that, say, took particles into meshes or into grids, 3D grids, both sparse and dense. We could have all that extra data flowing along with interpolation, and it created some nice workflows. But then it's like, okay, we have our data in this nice format, and it's like, oh, let's look at all the scientific software out there. Can we connect it? And it's like, oh, now we're back at a level where it's like it's not automatic, it's not connected nicely. So that leads to looking at stuff like NumPy and SciPy, which has a lot of that and has a general basis for doing those connections. So the SciPy library has been very successful at connecting people to a host of libraries. And that's where it started. It was like Travis and Eric and a few other people sort of bundled together a bunch of libraries that they felt were at the core of what they wanted to do in scientific computing, and provided that to Python. Tremendous service, and it's been very good for Python, very good for scientific computing, very good for science. So what about all the other languages? One thing that I've experienced, which is a little bit funny, is in some cases it's easier to just install SciPy and use a library from Python than it is to take that language or that library and use it directly in the original language it was implemented in, which is a little bit funny. It's like, that shouldn't be. It should be easy to use these libraries everywhere, I would hope. So another example of something that's happened within the scientific Python community is IPython has grown and then evolved and expanded beyond its Python roots. So initially it was the scratching of an itch, wanting interactive computing within Python, connected to NumPy and all of the other libraries there. And more recently it's evolved into a set of protocols and standards and software implementing those standards, written in such a way that people in other languages can connect to it and also follow those standards and then participate in an ecosystem. And it's not only the Python community benefiting, but it's other communities. And we as the Python community are getting the benefit of their input into it as well. It's a bigger boat for all of us. So this is really successful, and they're doing amazing work. So for something like NumPy, which is at a lower level, what's the equivalent for that? How can we both export the things that we've learned in doing NumPy and SciPy, and how can we connect to a broader community and get stuff back from them? So I think it's going to be protocols and standards and software implementing those, very similar to what the IPython folks have done. And I'll call that dynamic array infrastructure. It's like sort of the foundation, like NumPy is dynamic array infrastructure for Python. And we've used that to build a huge set of libraries, and it's fantastic. But maybe we could do better and have, like, share with even more people. So this isn't original at all. Like stuff like COM and Corba is similar, but in kind of a more general programming languages context, and operating systems, and how do you interoperate languages? It's a hard problem. So PEP 3118 is kind of doing that within the scope of NumPy. It's like, sure, we can interoperate by converting to Python and types and back, but this lets different plugins communicate without, like, depending on NumPy and things like that. So you could think of dynamic array infrastructure would be like PEP 3118, but it would sit even lower. And DARPA, its Xdata project, had a sub-project called XLang, which had some goals, or has some goals that are very similar to this. And they were inspired by this article in ACMQ that does a very good job of summarizing the problems and what you have to do to do this. So you have different object models, different runtimes. There's a lot of things. So we'll take a little bit of a detour through some software architecture ideas. There's a PyOhio talk by Brandon Rhodes, which you can watch it online. A very good talk that goes over some old software architecture ideas and shows, like, how you can apply them in Python. And the essence of it is that if you make your programs so that you have isolated and simple data, and you connect it with transforms, in particular like pure functions, your program becomes much more understandable and it's easier to test. Things become more orthogonal. Another similar talk but from a very different angle, is this talk from CVPCon, which is also online, which is about data-oriented design, which is coming from the game industry, where they really care about cache performance and a lot of things like that. So there, it's the same idea, but now you're caring about the specific binary layouts of everything. And there's some principles that they have, like that the purpose of all programs is to transform data from one format to another. Every program is doing that. And if you think of it that way and you understand the data at those edges and make that well-defined, that lets you understand things better and optimize things better. So for that, you have two essential pieces, the data and the code. And in NumPy, you have the ND array and the ufunc. This is a common thing, and these are the two pieces basically we need to create to have dynamic array infrastructure. So there's a lot of goals you'll want, or you need to accomplish to make it sit at the low level. You don't have a runtime to depend on. You can't use someone else's type system. You can't do a lot of things. Similarly, with sharing code, it becomes difficult. Like basically, you can rely on only the C ABI to be there. And everything else you have to define in such a way that people will be able to understand what your data looks like with just that level of access. And the foundation of that is the types. Like, how do you describe the data? How do you describe what code does? Because code is transforming data from one form to another. You need to know what that looks like to be able to do array-oriented computing and make things fast and connect, like, basically do the same thing many times. The type information lets you optimize that. So I'll quickly go over how DyND types and the DyND system tries to tackle that. So it's primarily a structural type system with D types that are very similar to the NumPy D types that you're familiar with. The representation is data shape. We've got a spelling that came out of the Blaze project, and it's extensible. It's kind of got a basic framework for that, plus syntax sugar for a lot of the common ways you structure your types. And an important thing is that if you have a concrete type, that maps down to a default memory layout of what that is. And it's also, it's predictable. So if you have like a 64-bit aligned type, you know how that, you can predict how that's going to combine with other types if you make a structure or a tuple or things like that. So here's kind of our basics. Just all of your scalars, very similar to NumPy. We've got an option type. So this is incomplete. A lot of this is incomplete, but kind of we've got a simple spelling, and we've got some ideas of how we can connect to Python with that. But the Pandas project is experimenting with this, and I think the feedback from Pandas to us of like, how should this look, is going to really define what we have to do here. It's not, it shouldn't be an abstract choice that it's like, it feels right to the developers of DyND. So dimensions are not a separate thing in shape. They go right in the type system. And basically, so you can think of two instances of a variable dimension of a float type is a kind of thing you can express. So then you can compose types. This is showing how a tuple type looks, or a struct type. If you've seen some of the Blaze talks, we're basically using the same language, except in DyND, we're defining it all the way down to the bit level. And finally, especially for type signatures, you need symbolic types, because you want to match whole classes of input types and like pattern match that, construct the output type based on that. So these are sort of some of the primitives that you can use for that. So one of the last things I'm going to do here is show how you can create a GU func in C++ for DyND. And it's basically defining your function and 2 lines of code. So we've got a function that accepts a size 3 array of doubles. And we just say, hey, turn that into an array function for DyND. And we're passing it as template arguments directly. And what that does is it gives the C++ compiler the address of that function at compile time, which means it can actually inline it when it constructs the loops for the inner loops. There's some crazy template metaprogramming and stuff going behind the scenes there. But in the end, it lets you express this very simply. And then we say, oh, let's take that function and apply it element-wise. So now it's broadcast. It's a U-func. So at first, it was like a function that took 3 floats and gave you a float. And then we applied element-wise, and now we have broadcasting dimensions. And so this dims ... is one of the symbolic ways to say those types broadcast. And then we apply the function, and very simple. Unfortunately, that equivalent isn't in Python. It's kind of, I know it's backwards that it's currently simpler in C++ than it is in Python to do this, but we're working on that. And Continuum has done a proof of concept of creating an rfunc with Numba, so you should be able, once that's all hooked up, good speeds and easy writing of these functions. So last slide, we've gotten a lot of support from Continuum Analytics and through a DARPA Xdata grant, and this summer we've got a Google Summer of Code, which has been awesome. So yeah, thanks for your attention, and that's it. Yeah, I think this is like lower level than that, but like I think the pieces that we're talking about building here could be the foundation for what you build a data frame like thing out of. So like a data frame, you probably generally want it to be column oriented and to have various semantics attached to it that are more than just implied by, like, it's an array of floats with a name. I mean, you want to do certain analyses, and layering that on top of DyND, I think would make a lot of sense. Yeah. A similar thing would be like if you want to do sparse matrices. It's like I don't think that goes right at the bottom level, but sparse matrices are made out of dense array components, and it's the same kind of thing, that those become layers on top of the infrastructure level. I have, what my hope kind of is that we can find a way to express that in the type system. Same with labels and other things like that. I mean, there's the parts of like how does that get expressed in the type objects, and how do you spell that in the data shape system? And neither of those have been sorted out or anything. We haven't produced any proof of concepts, but that's how I would like to tackle that. Yeah.
So you talked about sort of this vision of the common infrastructure across languages.
Mm-hmm.
So obviously, I mean, you can only do so much at once, and it seems like right now you're focusing on C++ and Python.
Yes.
But is there a plan to have a C API for this? Do you think there's some kind of long-term prospects for like R or Julia actually using this, or like what would need to happen?
Yeah. So definitely, yeah. A C API would make a lot of sense. During development, though, So we're implementing it in C++, and whenever you change stuff, all of the things you've built on top of it and where places you've connected it change, and so it creates it slows down development to hook too much up too soon. So right now we're, yeah. So I think to effectively do that, we need to define to the bytes exactly what's going on under the hood, and the C++ implementation should implement that, as opposed to just implementing something in C++ and it's like, oh, that's what we're wrapping. And by doing that, we'll have a protocol, a specification that's not dependent on the C++ ABI, which is where a lot of the trouble can come from doing that. And then in other languages, you can say write directly to the spec and be like, okay, I'm going to implement something that follows what they've said it does. And if we've done our jobs right, then we will interoperate. And others might choose to wrap the C++ library and use that as how you get things in there. So.
What I would expect from data frames are things like labels and annotations. I haven't seen that in your design. Have you thought about it? Or?
Yeah, similar to the units thing. It's like, I think that could go in the types somehow. I mean, that's a bit of a, how do you spell that problem? And how do you make it easily programmatically accessible in the type objects? And how do you I think I hope that approach will work. But I'm not sure when we'll start trying to implement those kinds of things. Sorry, say again.
Do you have any idea or hopes for the timeline for this?
Yeah, so right now, Erwin is basically working full-time on the project, and he's been, so that the C++ example I showed of 2-line GU func, that's big credit to him for doing that. And he's right now his mission is to make it usable for the experimental pandas integration and other things like that within month, 2-month time frame. Multiple languages, really low level infrastructure, that's really hard to say, because we have to build out functionality, and then we have to circle back and basically audit that low level and write spec documents and sort of start to freeze things at that point. And it's hard to predict how will features like units and labels and all of that stuff impact that. And it's sort of, I think we have to start going in those directions before we start solidifying towards a 1.0 too.
Maybe last question. Do you have an approach for user D-type? So can someone else write a new D-type design and it will just work?
So right now, the way it's implemented is you can write a user D-type in C++, and you have to build it with DyND. It doesn't have a dynamic linking way that will work well. There's not a dynamic registration of a new type ID, but similar to the protocols of well, how does your data look and stuff, and how NumPy's D-type extension works. I think it would be a similar idea. You would register a new type ID and then implement all the basic operations, I think, as these array functions, and then DyND would map on top of that. And so yeah, so in NumPy, in the NumPy box and places, we were talking about, well, where do NumPy's D-types go? So if that can be specified in terms of Python functions, and then you could numbify them into low-level code that follows this protocol, that would be something that would be pretty awesome and maybe long-term, but that's the kind of thing that could work.
Maybe